Agriculture is a major source of income in much of the developing world, and technologies that improve productivity can spur economic growth and alleviate poverty. But despite the benefits, adoption can be frustratingly slow, and a key concern is technology diffusion. How can policymakers induce widespread adoption of a new technology? This paper considers the role of social relationships. Friends and acquaintances may be a key channel through which individuals learn about, and are convinced to adopt, new technologies. This suggests that if we know the pattern of social connections within a network, we can potentially identify key individuals such that seeding a technology with them achieves maximal diffusion. In other words, network theory-based targeting might increase technology adoption. The authors test this using a randomized controlled trial conducted with the Malawi Ministry of Agriculture. The objective was to promote the use of pit planting, a practice that can significantly improve agricultural yields. To promote new technologies, the ministry relies on agricultural extension agents who travel to villages to seed technologies with a small number of lead farmers. These individuals, in turn, are trained to disseminate their knowledge via social learning. The experiment tested different strategies for choosing seed farmers, but kept all other aspects of the training constant. To start, a social network census was conducted in each of the study's 200 villages. Individuals were asked who they consult when making agricultural decisions, and their responses map the network of relationships in each village. Next, villages were randomly assigned to one of 4 treatment groups. In benchmark villages, extension agents used their normal criteria to select 2 seed farmers. In the remaining groups, the authors strategically chose seeds. In groups 2 and 3, targeting was done by running simulations over each village's social network data and identifying the theoretically optimal seed farmers that would maximize diffusion over a 4-year period. In Group 2, the simulations assumed a process of simple contagion in which individuals needed to know only one knowledgeable farmer for technology to diffuse. In this case, the optimal configuration typically had one network central seed to diffuse to the dense part of the network, and one more distant seed to diffuse to the periphery. Group 3 assumed a process of complex contagion, in which individuals needed to know at least 2 knowledgeable farmers. Here, the optimal seeds were usually both centrally located so as to maximize diffusion in the dense part of the network. Finally, the last treatment assumed complex contagion, but used farmers' geographic location to proxy for their position in the social network. These seeds typically had low centrality, but were close to one another in the network. And the results show that strategically seeding technology with network central farmers led to higher adoption. During the 3-year period of the experiment, pit planting adoption grew from 0 to 11% in villages in the complex treatment. Adoption rates were 3 percentage points lower in benchmark villages. Notably, targeting central farmers was especially important for avoiding the scenario in which no farmers adopted at all. This figure shows the percent of villages in each treatment group that had at least some adoption by non-seed farmers in years 2 and 3 of the experiment. For example, in year 2, diffusion had started in 42% of benchmark villages. These patterns reveal a key failure of expert-based seeding. Only 54% of benchmark villages had any adoption. Put another way, after 3 years, 45% of benchmark villages still had no non-seed adoption, and diffusion appeared to have permanently stalled. In contrast, villages with 2 central seeds had a 56% greater likelihood that at least one non-seed farmer adopted the technology. So, why did targeting central seeds matter for diffusion? The paper argues one explanation is that learning in this setting is actually characterized by complex contagion. When individuals need to have more than one informed connection, diffusion can be slow or permanently stalled. Overcoming this requires targeting central individuals. To provide evidence of complex learning, the authors use simulations to predict what diffusion would look like for each treatment group under the assumption of either simple or complex contagion. This figure shows the results. As seen before, these are the actual adoption patterns observed for each treatment group in years 2 and 3 of the experiment. To this, we add the simulated results when learning is assumed to be either simple or complex. So, for example, this bar indicates that if learning is simple, over 80% of benchmark villages are predicted to have some diffusion by year 2. This figure reveals several interesting patterns. First, when diffusion is governed by simple contagion, targeting is not very important. Regardless of how seeds are chosen, the majority of villages should experience some diffusion within 3 years. The picture is very different if learning is complex. These simulations show that many initial seedings lead to stalled diffusion, and diffusion is much higher when central seeds are targeted. Overall, when comparing the simulations to the actual results, we see that the observed empirical patterns are more consistent with a complex learning environment. In line with this, farmers who were connected to 2 seeds in the experiment were more likely to learn about and adopt pit planting than farmers connected to only 1 seed. Thus, technology diffusion can be accelerated by targeting network-central individuals. On a practical note, while collecting network data may be too costly in many scenarios, other papers have explored cost-effective ways to learn about a social network's structure. This suggests that network-based targeting can be a feasible approach in policy settings. To read more on this topic, you can check out the paper's references to other related work. These include papers on technology adoption, networks, and identifying central individuals.